Here we are going to derive the relation for natural frequency of transverse vibration in a beam. First of all, what is a beam? Beam are the structure element which are used to support the load, and beam has infinite degree of freedoms, and so it has infinite number of natural frequencies. But in practical point of view, only lower frequencies are important. So here we are going for the derivation. So first of all, suppose this is the beam and it has a radius of curvature r. This is the r is the radius of curvature of this beam. ds, we will take a small element ds for the analysis, frequency analysis. We will take a small element ds which is at an angle of theta, and length of this element subtend angle d theta at point O or at center of curvature. Now we have enlarged this small element here. It is a distance from this point to this point. Length of the element is ds and it subtends angle d theta. Radius of curvature of this element is r. So as the d theta is very small, so we can take ds from this point to this point. This distance is equal to dx. But as we know, for in a circle, suppose this is the radius r, this is the angle theta, and this is the arc length at L, then theta is equal to L by r. Similarly, we can find this ds is equal to r into d theta. So ds is equal to r into d theta. So but ds is equal to dx. So this dx is equal to r d theta. So this is about the diagram. So now we'll go further. So first of all, we will let the small element ds vibrate with simple harmonic motion. Now as with simple harmonic motion, x is equal to a sine omega t, that is a sine omega t. So this is the x is the displacement of this element at any time t. So x dot velocity of this element, linear velocity of this element is equal to v is equal to x dot. So v is equal to x dot is equal to dx by dt. We will take the differentiation of this equation. We will get the velocity of this element. So this will be equal to A omega cos omega t. So maximum velocity, this velocity will be maximum when the value of cos 2 theta is equal to maximum, and this maximum value is equal to 1. The value of the cos omega t, maximum value of cos omega t is 1. So maximum velocity of this element, maximum velocity of element is equal to A omega n, where omega n is the natural frequency of this element. But displacement of this element from the mean position, this is equal to dy, this is equal to y, this is equal to y. From the mean position, this displacement is equal to, this is equal to x, and this is equal to y. Now maximum kinetic energy of small element is equal to half m mass of element maximum kinetic energy is equal to half m into v maximum square, half m square. V is the maximum, so maximum kinetic energy is equal to half mass of body into its maximum velocity, square of its maximum velocity. Hence maximum kinetic energy of element will become half mass of this element dm dm is the mass of small element into Vmax. Vmax is equal to, we have already calculated, A omega whole square, but amplitude A is equal to y. So kinetic energy of this element is equal to half dm into y square into omega square. So this is then kinetic energy of beam will be the integration of 1 by 2 dm into y square into omega square, which is equal to half omega square integration y square into dm. This is our equation number 1. This is the maximum kinetic energy of the beam. Maximum kinetic energy of the beam. Second is, due to this bending, energy will be stored in the beam, and strain energy is equal to strain energy is equal to half into bending moment into angle in radian. This is equal to half into m into theta. So strain energy stored in this small element, strain energy in small element is equal to half m into d theta. And strain energy stored in whole beam is the integration of this equation, half into m into d theta. This is the equation number 2. Usually this deflection in the beam is very, very small. So we will take theta is equal to dy by dx, and we are also known dx is equal to, we also, dx is equal to r d theta, r d theta, as we have already explained. From this equation, 1 by r is equal to d theta by dx. This implies 1 by r is equal to d by dx into, we will put the value of theta, and theta is equal to dy by dx, dy by dx. So 1 by r is equal to d square y by dx square. This is equation number 3, and this is equation number 4. As we already studied the relation in strength of material subject in bending of beams, that the relation is m by I is equal to E by R, where m is the